Hello, my name is Fuxin Li. I'm going to present our work PointConvFormer, Revenge of the Point-Based Convolution. This is a joint effort by Wenxuan, myself, and Shan. This work is done within Apple. In recent years, there has been a significant amount of sensors that can directly generate depth information, such as the Kinect and LiDAR sensors that are used in indoor and outdoor scenarios, respectively. Hence, 3D point clouds have become much more important as the input modality for 3D recognition tasks. In this paper, we present PointConvFormer, which is a new recognition backbone on point clouds motivated by learning theory. It combines ideas from point convolutions and transformers to achieve a better accuracy and runtime trade-off than sparse convolutions across semantic segmentation and scene flow tasks. It achieves such with almost 10 times less parameters than sparse convolutions and faster than old point-based approaches. There are usually two mainstream types of point cloud backbones. The first is sparse 3D convolution, which is similar to regular convolutions, using 3x3x3 neighborhoods usually. The difference is that they usually will not make any computation if the center point is unoccupied, hence maintaining the sparsity pattern before and after the convolution. Because of the sparsity in their neighborhoods, they might not be good in capturing fine details. Another type of network is point-based methods, which usually rely on k-nearest neighbors or an epsilon ball to gather a neighborhood. However, the neighborhood could be irregular or have different number of points. And that's why when we started the research, point-based approaches were usually not able to obtain accuracy as good as sparse convolutions, such as Minkowski network. So our idea here is that we want to try to filter out some of these irregular neighborhoods so that we end up with some good neighborhoods that are more regular so that we can improve the performance. The idea here is to use ideas from attention-based models that are very popular recently in natural language processing and computer vision. Those attention-based methods compute attention between many token pairs, and with the softmax activation, finally only a few tokens get activated, and the other tokens essentially get filtered out, which is exactly what we want to achieve. So we want to basically try to incorporate that into our convolution formulation. Let's look at some technical details. So we start from PointConv, which is a point-based convolution formulation. It has two main ideas. The first idea is to discretize a continuous convolution to summation over points in the neighborhood of a point P. So the second idea is that we try to approximate this convolution function W of Pi minus P as a multi-layer perceptron starting from the relative position Pi minus P. This W can be written as two parts. W2 is the last linear layer, and M is all the previous layers. We note that we can extract W2 outside of the summation sign, which leads to only M times X inside the summation sign. This is nice because M can be of much lower dimensionality than W2, allowing us to save a significant amount of computation and model size. We can also append rotation and scale invariant coordinate transforms into the Pi minus P so that the network can learn to be invariant to scale and rotation if necessary. So our goal is to try to incorporate attention into PointConv, and then we can check their formulation first to see the similarity and differences. The similarity lies in that they both use the relative position encoding. And then W2 is also similar in PointConv and attention-based models, which usually have a linear layer after the attention-based model. The difference is that the attention-based models have this Q times K term, which works on feature similarity. So similar features can help us to retain important or relevant points, and dissimilar features can help us to filter out irrelevant points. So in our new formulation, we add this aspect to the point-based convolution, where we add a psi in the middle of the point-based convolution that takes inputs of the feature similarity as well as the location similarity. That helps us to turn off certain irrelevant features, whereas it maintains the capability of PointConv to incorporate scale and rotation invariances because it maintains the formulation M of Pi minus P. In terms of building a network, an encoder-decoder network with PointConvFormer, we also need downsampling and upsampling methods. For downsampling, we use grid downsampling as in KPConv, and for upsampling, we just use PointConv, which allows to upsample to locations that does not have any features. There are some other implementation details, including using ResNet-style bottleneck layers for downsample to 1/4 of the channel dimension, compute PointConvFormer, and then upsample, as well as the lightweight decoder, which we use a channel expansion ratio of only 1 in the decoder layers. This helps us to save a significant amount of parameters with almost 0 accuracy loss. With that, we get to this performance of PointConvFormer, which is, in terms of accuracy, a bit better than sparse convolutions such as Minkowski network. In terms of speed, it's comparable. In terms of model size, PointConvFormer is usually 6 to 7 times smaller than Minkowski networks because they generate filters dynamically rather than have fixed 3x3x3 convolution filters. In terms of comparing with previous work, we can see that we perform better in both accuracy as well as better runtime with previous point-based methods. In outdoor scenes, we also outperform Minkowski network by a significant margin, as well as outperforming some other point plus voxel fusion methods in the past. In terms of ablation, we show that using PointConvFormer style of using attention to modify convolution is better than other type of attention models. We also show results on SynFlow, where we replace the PointConv in PointPWCnet with PointConvFormer, and then we show there's also very significant improvements over there. In this visualization, we visualize the maximal difference between the highest attention and lowest attention in the neighborhood. So blue would indicate that there is almost no difference and PointConvFormer is similar to convolution, and the red would indicate there's like a large difference and PointConvFormer performed a lot of neighborhood filtering. It can be seen that at object boundaries, this neighborhood filtering is stronger, and inside the object is more similar to convolution. This is similar to the goal that we stated earlier. So now we can revisit the voxel point debate. If we use sparse convolution, then we can use the regular 3x3x3 neighborhood. However, a point-based representation allows us to incorporate rotation and scale invariance, as well as using the attention to alleviate the issue of KNN. So with that, we believe point-based methods can be more attractive in the future, given this work. And welcome to come to our poster so that we can discuss further. Thank you very much.